All right. This is section 9 of Unit 8. This is calculating electric field from non-uniform charge density. So this is kind of throwing everything together, Gauss's law, and all that fun stuff to figure out electric field from non-uniform charge density. So we previously had only been looking at the uniform density and the discrete charges. Now we're doing it with non-uniform density, which is going to take a little bit more effort to get to. Okay, this section's kind of long just because there's so many graphic organizers. I'm not going to use all of them. I'm probably just going to use the first one and then be done with it, because you're actually going to do most of the work already in the first section. Okay. Charge density is not uniform. It varies with this function right here. Rho equals rho naught times capital R over little r, where little r is the distance from the center of the sphere that we're going to pick. Okay. Answer all the following in terms of rho naught, r, and fundamental constants. Determine the amount of charge enclosed within a sphere of radius r, where r is greater than big R. So this is going to be in a let me just draw this in a radius that is larger than the sphere itself. Okay, so first I need to figure out the enclosed charge by the sphere, and I do not know the total enclosed charge, but what I can do is I can actually integrate this function to get the total enclosed charge. So I'm going to integrate rho with respect to volume. Okay, this is a volume charge density. Okay, it's not uniform, but it's volume charge density. So then what I can do is I just gotta incorporate. I gotta plug in all my stuff here. This is going to be rho naught capital R over lowercase r. The volume that's being integrate that I'm integrating through is going to be I can re-express the volume as 4 pi r squared times dr, okay, because that's the surface area that we're integrating through, okay. Um, and this is should be integral. Sorry, I should have the integral sign in the front here. And this will turn us into enclosed equals, I can factor out the 4 pi rho naught capital R. And then my bounds, I'm going to go from 0 to R, okay, which is going to be the distance out here, okay, of R dr, okay. And so all I need to do, okay, is I'm going to go from 0 to r on this integral right here. This is a pretty easy integral to do. This ends up giving me q enclosed is equal to 4 pi rho naught capital R times 1/2 r to the r squared. Okay, and the zero bound is going to be the bound of 0 when I plug that in is just going to turn this into 0. So I can that's all I have to do for the integral right there. Okay, and then I can simplify this a little bit more. I can turn this into q enclosed is equal to 2 pi rho naught times capital R little r squared, and that is actually just going to be my enclosed charge. Okay, I don't have to go any further than that. Okay. Determine the total amount of charge within the sphere, then write an expression for the electric field as a function of r if little r is greater than big R. So this is going to be, again, still outside the sphere. Okay. All I need to do is I take my above function and I'm going to set little r equal to capital R in the q enclosed function. Okay, so all I have to do is set little r equal to big R, and that's just going to turn this into big R cubed. Okay, so that's going to be q enclosed, or sorry, q total, sorry, is going to be equal to 2 pi rho naught times capital R cubed. Okay, that's my total charge enclosed. Okay, and then to get the electric field, all I have to do is do the surface integral E dot dA equals Q enclosed over epsilon naught. And now what I need to do is Q enclosed is going to be all of the charge. It's going to be all of the charge. So I'm just going to take this whole total right here and plug it into Q enclosed. The surface area that it's flowing through is going to be for the sphere. It's always the same for the sphere. 4 pi r squared, okay, equals 2 pi rho naught capital R cubed over epsilon naught. Okay. This r is the radius of as the radius of the sphere. We can leave it like that. Okay. And then is a radius that we're picking. So we don't want this to be. This is not going to be the same as this r right here. And we can cancel out some stuff. We'll be left with the pi's cancel out. We'll be left with a 2 on this side right here. And then when we divide it, we end up getting that the E field is equal to rho naught times r cubed over 2 little r squared times epsilon naught. Okay? So that should be our E field equation right there. Okay? Okay, write the expression for the electric field as a function of r if r is less than capital R. Okay. I've actually already solved this out for the most part. Okay. The reason, and you can fill this out on the graphic organizer. I'm not going to though, because there's no real reason to, and you have to learn how to get yourself off of the graphic organizer anyway, right? Because you're not going to have that on the test and everything like that. An expression for the electric field as a function of r if little r is less than big R. That's going to be the surface integral E dot dA is equal to Q enclosed over epsilon naught. Okay. And this is going to be only the charge. We want this part up here, the Q enclosed. This needs to be only the charge enclosed by the sphere of radius little r such that it's less than big R. Okay, so we don't want the whole charge. We just want the and that's going to be the enclosed charge that we solved at the very beginning. The 2 pi rho naught capital R little r squared. Okay, so we're just going to plug that into that. The dA we've already figured out. Okay, this is just going to be E dot 4 pi r squared equals 2 pi rho naught capital R little r squared over epsilon naught. Okay. And when we solve this out, okay, you can see that a lot of stuff's going to cancel here. This is going to turn into 2. This is going to cancel out over here. And then r squared is going to cancel out with the r squared over there. Okay, and you should end up getting a really nice, nicer looking equation, which is rho naught r over 2 epsilon naught. Okay. So that's. I mean, you know, you could solve that using the graphic organizer if you want. I didn't do it with the graphic organizer because you do have to kind of train yourself off of it. But there's that. Okay. And then to do the graph, you're going to notice that as you move, the E field is a constant. It is not dependent on. Is only a little bit dependent on little r, right? But what you're going to notice is that the this actually right here, if you are inside of the conductor, okay, then this little r is going to be this little r actually cancels out with some of your r on the top here. So this actually could look like rho naught r over 2 epsilon naught if you're looking at it. Oh wait, no, sorry, that's what we got down here. Okay, if we're looking right here, this is when we're inside of the sphere, right? This right here is a constant. It's not dependent on little r whatsoever. So this is just going to be a flat line until you hit the surface of the sphere, then it changes, okay, to the inverse square relationship that we see in the part up here, okay? So it's probably going to, look something kind of like this. It's probably going to look a little wonky, but yeah, okay? That's probably something about what it would look like, okay? You'll notice that the value up here is just going to be equal to the rho naught r over 2 epsilon naught, which is what we got there, and then it'll decrease exponentially down, okay, inverse square. Okay, this is the graphic organizer. The main thing I want to go over is how did I get the enclosed charge. You do have to integrate to get the enclosed charge. The volume of the enclosing surface we picked was 4/3 pi r cubed. And if you integrate that, or sorry, if you differentiate that to get the differential volume, you actually end up getting 4 pi r squared dr. That is literally that's literally all you have to do for that. Okay. And that's also the surface area too. Isn't that interesting to think about how when you differentiate the volume, you get the surface area? And that actually works, I think, for the other shapes that we're going to look at too, off the top of my head. That actually works. Okay. And then that's why we were able to plug that in for dV in the previous part over there. Okay. So we're taking the volume, we're differentiating it, and we get dV. Okay. And then you plug that back into the equation and solve everything else. I'm going to solve these without using the organizers because I do not need to use the organizers to solve these. They're not that terrible, okay? They're not that bad to solve without the organizers. If you want to use them, you can plug everything in if you want, but I'm going to show you every step how to do it. I need to first figure out, the first step is always to figure out your enclosed charge, okay? Q enclosed. In this case, I'm going to integrate this function right here, CR to the n, okay? So this is going to be the integral of the rho with respect to volume, okay? And I'm going to do, is the integral of CR to the n. I'm going to change dV to be my differential volume, which is my surface area, dr, okay? So then it would be 4 pi r squared dr. Now I have an integral in terms of r, okay? Or sorry, in terms of r, okay, not n, it's r. And I can factor out my constants now to make this a lot easier for me. I can do 4 pi c integral of r to the n times r to the second dr, okay? And this will become r to the n plus 2, okay? And then you can take the integral of that. The bounds, they should be set from 0 to r, okay? Just like this is pretty much how it's always going to be. For the other examples, it's going to look like that too. This is going to turn into Q enclosed is going to be equal to 4 pi c times r to the n plus 3 over n plus 3, okay? Because this becomes n times 2, and then when you integrate it, you increment the exponent by 1. Okay, so there's my Q enclosed. Now I just need to solve the actual Gauss's law. Integral, or surface integral of E dot dr is, or sorry, dA, sorry, is going to be equal to Q enclosed over epsilon naught. Okay, all I got to do is now plug in everything. This integral for a sphere is always going to be E dot 4 pi r squared. And then Q enclosed I just solved earlier is this whole mess right here. This is going to become 4 pi c r to the n plus 3 over epsilon naught times n plus 3. Okay. And thankfully, there's quite a bit of stuff that can cancel out here so that we don't have to actually divide everything because this just may be a mess. 4 cancels out, pi cancels out, and then we have r squared. That'll actually cancel out here to give us n plus 1 in the numerator. Or sorry, in the exponent, okay? And this ends up being the electric field is equal to CR to the n plus 1 over epsilon naught times n plus 3. Okay? So that is going to be my electric field for that. I don't actually, notice how how I did step by step, just like in the organizer, but I didn't actually have to use the organizer for that. Okay. A cylinder that is very long and has a uniform volume charge density that varies with radius is given by this function, where n can be any real number. Use Gauss's law to determine the electric field within the cylinder as a function of r. Draw a picture and explain each step. Perfect. The volume of a cylinder, right, we all know is pi r squared times L. That's the circumference of the circular base, and we multiply it by the length so that we basically stack the circle on top of each other over and over. And then when we do the differential volume, dV, and we differentiate that with respect to r, that's going to give us 2 pi RL dr. Okay. So now we can plug that into the Q enclosed formula. Integral of CR to the nth power times 2 pi RL dr. This is going to look pretty similar to what we got earlier because you can see we can factor out quite a bit. So we can do Q enclosed equals, and if I factor out my constants, I get 2 pi L. Sorry, I don't want to take R out yet. 2 pi C L. Okay. Times the integral of R to the nth power times R dr. And this goes from 0 to R. Okay. Okay. This is going to look very similar to what we had before. This is just going to turn into the Q enclosed is going to be 2 pi CL times R to the n plus 3 over n plus 2. Oh, sorry, it should be just n plus 2 on the top here, okay? Okay, so it's going to look very similar to what we had before, but it is going to be a little bit different, okay? Now, when we determine the electric field, okay, surface integral dot dA equals Q enclosed over epsilon naught, okay? Then okay, so then this is going to become the E, and for cylinder, it's always going to be 2 pi RL equals Q enclosed, which I already got was 2 pi CL R to the n plus 2 over epsilon naught times n plus 2. And my hand hurts because I'm writing so much stuff, right? 2 cancels out with each other, pi cancels out with each other, r cancels out up here to give us n plus 1, and then L cancels out here too. So we actually completely eliminated the left-hand side except for E, and then we can solve for what E is going to be equal to. This is going to be CR to the n plus 1 over epsilon naught times n plus 2. Okay? So there you go. That's the E field through the cylinder, through a non-uniform cylinder. Now, if we have a non-uniform slab, okay, we're going to do this was, we use the Gaussian surface of a cylinder, and then first we use a sphere, then a cylinder. Now we're going to use the rectangular prism, okay? And this is going to be, our volume, our volume is going to be A times X. I'm going to use that's the area of the base times X, which is the height, okay? The differential volume is simply just going to be A dx. Okay. So when I plug this into the Q enclosed, okay, I'm going to do the integral of C times X to the nth power times A dx. And this is actually probably the easiest of the integrals to do because there's not like another X term in there somewhere. This just becomes, we can factor out the C and the A. CA integral of X to the nth power dx. And then this becomes Q enclosed equals CA times X to the n plus 1th power over n plus 1. Okay? Okay, and then when we plug that into the surface integral, the actual Gauss's law part, okay, E dot dx, or dA, okay, equals Q enclosed over epsilon naught, okay, then the area that is the flux is going through is going to be A. Okay. The reason why it's just going to be 1A is because when we draw our surface, it's literally going to kind of cut the slab in half. Okay. So we're doing this sort of thing. You know, we're not like doing the whole slab. We're cutting halfway through it because if we did the whole slab, it should end up being 0, right? So then this is going to be E dot A equals the enclosed charge CAX to the n plus 1 over epsilon naught times n plus 1. And then you'll notice that your A's cancel out, and this is also super, super simple. Okay, you get the E field is equal to CX to the n plus 1 over epsilon naught times n plus 1. Okay, beautiful, incredible. Okay, the pattern that we are getting from this is if density, okay, varies with r to the n or x to the n, okay, E field will vary, okay, with r to the n plus 1 or x to the n plus 1, regardless of shape. This is one way that you can kind of self-check yourself, is recognize that if the density is r to the n or x to the n, the E field will vary with r to the n plus 1 or x to the n plus 1, doesn't matter what shape it is. Okay, so if you end up like getting something that matches that, then you know you're probably on the right track. If you get something that doesn't really match that, then maybe not so much. Okay, I believe, if I'm not mistaken, that should be the last of that section because it's just these organizers that I didn't do. Yeah, and we'll be back with the final section of unit 8 here in a moment.